What we're going to be talking about today is sums of radicals, and briefly, adding radicals is like adding similar terms. So it's just like combining like terms. When we're adding radicals, we're really combining like radicals. So for example, I have a polynomial equation right here. All I'm doing when I'm simplifying this is combining like terms. I have a 5x here and an x that gives me 6x. 3y minus 4y gives me negative 1y. When I am adding radicals, I'm really doing the same thing. So I have 5 square roots of 2 plus 3 square roots of 11 plus the square root of 2 minus 4 square roots of 11. I'm going to combine the radicals that are like. So 5 square roots of 2 and the square root of 2 are like radicals. They have the same square root. So 5 of them plus 1 of them gives me 6 square roots of 2. All right, that's essentially how we're going to add radicals. Now here I have 3 square roots of 11 and negative 4 square roots of 11. 3 plus negative 4 is negative 1. So I have negative 1 square root of 11. Now I cannot combine 6 square roots of 2 and a negative square root of 11 because they are not like radicals. So this is as simple as I can make this particular expression. That's as simple as I can make it. So when we're doing this, we'll go to our first example. There's a process you should go through because right now these are not like radicals. Square root of 27 is square root of 12. I cannot add them. This is as simple as I can add them. But here's what I want to do. Simplify each radical separately first, and that means using our product rule and our quotient rule. Then you can combine or add if the terms are similar. So that's what we're going to do. So these problems can take a while because you've got to simplify all the individual radicals. So I have to ask myself what perfect square goes into 27, and the answer to that is 9. 9 times 3. So I have the square root of 9 times the square root of 3. The square root of 9 is 3, so this is 3 square roots of 3. All right, I just used what we did last week and simplified that radical. With 12, I have to ask myself what perfect square divides evenly into 12, and that's 4. 4 times 3. So this is the square root of 4 times the square root of 3. The square root of 4 is 2, so this is plus 2 square roots of 3. Now I can see that these are like radicals. They both have the square root of 3. 3 of them plus 2 of them gives me 5 square roots of 3. All right, if we go to the next example, this actually looks like you should distribute this. And that is exactly what we're going to do. We're going to distribute. So we're going to use our product rule to do this. The square root of 6 times the square root of 2, we can put them under a single square root. That equals the square root of 12, because 6 times 2 is 12. Square root of 6 times the square root of 3 is the square root of 6 times 3, which is 18. Now we wouldn't want to leave this expression like this. What we want to do is make sure before we're done that we simplify all of our radicals, because this is not simplified until all of our radicals are simplified. So what perfect square goes into 12? That's 4. So this is the square root of 4 times the square root of 3, because 4 times 3 is 12. The square root of 4 is 2, so this is 2 square roots of 3. What perfect square goes into 18? That's 9. 9 times 2. So this is the square root of 9 times the square root of 2. The square root of 9 is 3. So this is plus 3 square roots of 2. And of course, I cannot combine those because they're not like radicals. One has the square root of 3, and the other one has the square root of 2. Now C, we're really doing the same thing. But what we've got to keep in mind here is our rules, okay? Our rules for adding and subtracting fractions. So first of all, what I'm going to do is use my quotient rule to split the top and the bottom into separate radicals, because these don't divide. So I have the square root of 32 over the square root of 3 plus the square root of 2 over the square root of 3. And of course, in order to add fractions, I need a common denominator, which I have. I do have a common denominator, the square root of 3. So I'm going to add across. This is the square root of 32 plus the square root of 2. I'll have to simplify that. And my denominator is the square root of 3. Now, in order to simplify this, let's look at the square root of 32. What perfect square goes into 32? The largest one is 16. All right? 16 times 2. So this is the square root of 16 times the square root of 2. And the square root of 16 is 4. So when we simplify this, we're going to have 4 square roots of 2 plus the square root of 2 over the square root of 3. All right? Now, we have like radicals in our numerator, so we can combine those. 4 square roots of 2 plus 1 square root of 2 gives us 5 square roots of 2. So we've got 5 square roots of 2 over the square root of 3. The only thing we got to remember is we can't leave a square root in the denominator. That means we'll have to rationalize our denominator. And in order to do that, we're going to use our denominator, the square root of 3, and we're going to multiply this fraction by 1. But 1 is going to look like this. The square root of 3 over the square root of 3. So in our numerator, when we multiply across, use our product rule. Square root of 2 times square root of 3 is square root of 6. So 5 square roots of 6. In our denominator, the square root of 3 times the square root of 3 is 3. So this one took an awful lot of work to get to the end. All right, I'm going to show you D, and I'm actually going to show you that this is actually easier than you might think. All right, what I'm noticing here, I have a 3 on the bottom. 21 divides by 3, and so does 15. They both divide by 3. If you have that situation, then there's an easy way to resolve this particular problem, and that is this. Write this as 2 separate fractions with the denominator of the square root of 3. So this is the square root of 21 over the square root of 3 plus the square root of 15 over the square root of 3. Use our quotient rule and make each of these fractions a single square root. So this is the square root of 21 over 3 plus the square root of 15 over 3. And both of these divide, which is why we use this particular method. 21 divided by 3 is 7, so this is the square root of 7. Plus 15 divided by 3 is 5, so this is the square root of 5. And neither the square root of 7 nor the square root of 5 is going to simplify any further, and so we're done. All right, let's take a look at E. E, we're just adding some radicals. The issue is here is in order to figure out if any of these are like radicals, because we can only combine them if they're like radicals, we're going to have to simplify all 3 of these radicals. All right? So square root of 50, what perfect square goes into that, is 25. So this is the square root of 25 times the square root of 2. All right, take a look at 245. I may not know right away what goes into 245, But remember my perfect square, so I can just go about trying some of these. So I tried 9, and 9 doesn't go in. 16 doesn't go in. 25 won't go in. 36 doesn't go in. 49 does. 49 times 5. So we're going to simplify this as the square root of 49 times the square root of 5. And the last one is 125, and I know this one by heart. 25 goes into this. This is 25 times 5. So the square root of 25 times the square root of 5. All right? So now what I've got to do is simplify. In my first term, I've got the square root of 25, which is 5, times the 2, which is 10. So this is 10 square roots of 2. Minus the square root of 49 is 7, so 7 square roots of 5. Here the square root of 25 is 5 times 3 is 15, so plus 15 square roots of 5. And now I can only combine those terms that are like, which is the 2 square roots of 5 here. So negative 7 plus 15 is positive 8. So I've got 10 square roots of 2 plus 8 square roots of 5. All right, let's turn the page. And we've got a problem that has some cube roots here. All right, still works the same way. So first of all, I've got the cube root of 81. So I need to know what perfect cube goes into 81, and that's 27. 27 times 3. So I have the cube root of 27 times the cube root of 3. The cube root of 27 is 3, so I have 3 cube roots of 3. Now, let's see. What perfect cube goes into 24? That's 8. 8 times 3. So the cube root of 8 times the cube root of 3. And the cube root of 8 is 2. So minus 2 cube root of 3. Now, they are like radicals. They're both the same. So 3 of them minus 2 of them leaves me with 1. So just the cube root of 3. All right, example B, same thing. It just happens to have some x's in it. All right, so here's what we're going to do. Simplify each of them, and then we're going to see what's going to combine. So out of 12, I can do this. Perfect square that goes into 12 is 4. 4 times 3. So I have the square root of 4 times the square root of 3. Now, I have x to the 5th. There's no square root of x to the 5th, but there is for x to the 4th. All right, because it's in even power. So I'm going to split it up into the square root of x to the 4th times the square root of x. When I simplify that, the square root of 4 will give me 2, and the square root of x to the 4th gives me x squared, because x squared times x squared is x to the 4th. All right? So in front, I've got 2x squared, and then I've got the square root of 3x. Okay, we've got to do the next one. So I've got an x, and I can't simplify the square root of 3, so I'm going to put that by itself. Can't simplify the square root of x to the 3rd, but I can simplify the square root of x squared. So I'm going to split it up into x squared and x. So square root of x squared times the square root of x. All right, now I'm going to simplify what I can. The square root of x squared is just x. So multiply what I have outside the square root is x times x, which gives me x squared. And then I've got the square root of 3x. All right, let's do the last of the three terms. So first of all, I've got a 5x squared. And then I have the square root of 3x, which there's nothing in there that I could simplify, so I'll just add it on the end. Plus 5x squared times the square root of 3x. Now, here's the thing that's different about this. Not only do you need to have a like radical to combine these, you also need them to be like terms in general. That means this whole part is the same as this whole part, is the same as this whole part. If this part in front, the x squared, isn't the same, they cannot be combined. It's part of the like term. So I've got two of them. Minus 1 gives me 1. Plus 5 gives me 6. So in the end, I have 6x squared square root of 3x. All right, the next example. Remember, in order for me to add or subtract fractions, I need to have a common denominator. I don't right now, because I have a square root of 2 here and a 1 here. So here's what I'll do. And of course, you could probably come up with a multitude of different ways to work out this problem. But what I'm going to do is multiply the top and bottom by the square root of 2 so that I have a common denominator. This is going to give me, with my product rule, the square root of 12y over the square root of 2 minus the square root of 3y over the square root of 2. Now, I have a common denominator, so I'm going to keep that and subtract across my numerator. So I have the square root of 12y minus the square root of 3y on top. I have the square root of 2 on the bottom. I just need to simplify my numerator. All right, so what perfect square goes into 12? That's 4. 4 times 3. So actually what I'll do is I'll have the square root of 4 times the square root of 3y, because that part won't simplify. The square root of 4 is 2, so this is 2 square roots of 3y minus the square root of 3y over the square root of 2. My next step, I have like radicals in my numerator, so I'm going to simplify them. 2 square roots of 3y minus 1 leaves me 1 square root of 3y in the numerator, and in the denominator, I'm left with the square root of 2. But remember, I can't leave a radical in the denominator, so I need to rationalize this. Use the square root of 2 in the denominator, multiply this fraction by 1 in the form of the square root of 2 over the square root of 2. Use my product rule as I multiply across. 3y times 2 is 6y, so this is the square root of 6y. Square root of 2 times square root of 2 is 2. And remember, I cannot cancel that 6 and the 2 because the 6 is under the square root, the 2 is not. All right, let's take a look at D. When we start out with D, if this just had x's in it, it would be a really easy problem. But it's not, because we've got radicals that we've got to simplify. What we're doing is distributing first and then combining like terms. So I have negative 4 times 3 is negative 12. Square root of 6 times square root of 2 is the square root of 12. Negative times negative will give me positive. 4 times 5 is 20. Square root of 6 times the square root of 3 is the square root of 18. Plus, then I have 5 square roots of 48. Now we need to simplify all three of these radicals to see if we can combine any like terms. So, square root of 12, 4 goes into 12, so this is the square root of 4 times the square root of 3. The square root of 4 is 2 times negative 12 is negative 24 square roots of 3. Next, I have the square root of 18. 9 goes into 18, so this is the square root of 9 times the square root of 2. The square root of 9 is 3 times 20 is 60, so plus 60 square roots of 2. Next, I have the square root of 48. The largest square that goes into 48 is 16. 16 times 3. So square root of 16 times the square root of 3. The square root of 16 is 4 times the 5 gives us 20 square roots of 3. Now I just combine the terms that are like, and I have two terms with the square root of 3. Negative 24 plus 20 gives me negative 4. So this is negative 4 square roots of 3 plus 60 square roots of 2. All right, one last example for today. Now, we're going to go back to this problem right here, where I said we have a special way we can do this if both these numbers divide by the denominator number, all right? These do. 40 divides by 8 and 24 divides by 8. So here's what we're going to do. We're going to split this part up into two separate fractions. So I have 3 times the square root of 40 over the square root of 8 plus 2 times the square root of 24 over the square root of 8 minus the square root of 5. Next, I'm going to use my quotient rule to put each of these under the same square root. So this is 3 times the square root of 40 over 8 plus 2 times the square root of 24 over 8 minus the square root of 5. Simplify my fractions. 40 divided by 8 is 5. So I've got 3 square roots of 5. 24 divided by 8 is 3 plus 2 square roots of 3 minus the square root of 5, and just combine those that are like, which is the square roots of 5. 3 of them minus 1 gives me 2 square roots of 5. So 2 square roots of 5 plus 2 square roots of 3. And we can't combine any further because they are not like radicals.